The third screencast here in Unit 2 is about tire marks and glass and how we analyze those. First of all, tire and tool marks can be found at a lot of different crime scenes, but the main ones we're going to be talking about are car collisions, hit and run, burglary, and breaking and entering. When we're analyzing tire marks and tool marks, what we're going to be doing in class is actually casting the tire marks. Those tire marks are going to be observed macroscopically when we take a look at them. If finer details need to be determined, you can actually observe the tire marks or tool marks microscopically as well. And then we do a comparison. The standard reference sample is the tires from a vehicle, and you're going to use that to compare to the tire treads from the crime scene. Tool marks would be, we're not going to work with tool marks in class, but you do that in the same manner. Tool marks, depending on what the tool has been used on in the past, will have different wear marks, different wear patterns, different imperfections once it leaves the store and is used. And so those unique imperfections to each tool mark can identify it and individualize it. A little bit of background information on glass. All glass is made from silicon oxide, which we commonly know as sand. Sand is basically heated to melting, and then we can add different sorts of metal oxides. So some sort of a metal, which is, if you think about the periodic table, the elements on the left-hand side of the periodic table, and those are chemically combined with oxygen. That's what a metal oxide is. So sand and then different metal oxides are melted and then cooled to make various kinds of glass. We're going to talk about 4 different types, main types of glass here in class. The first one is probably, I guess, the most generic, is the window and bottle glass. It contains sand, soda lime, and then, like I said, those metal oxides. So window glass and bottle glass, pretty simple, speaking in terms of glass. Auto headlights and heat-resistant glass like Pyrex, which is what you'd find with glass cookware. Anything that needs to withstand a lot of heat, boron oxide is added in addition to the previous 3 ingredients. Tempered glass, basketball backboard, patio tables, in autos, the side and rear auto windows, sliding glass doors. Anytime you want to prevent damage or bodily damage from a shattering of glass, you use tempered glass because it tends to form beads or rounded edges instead of jagged, sharp edges. So those tempered glass, what happens with that is it's rapidly heated and then cooled. And for whatever reason, with this rapid heating and cooling process, the shattering beads instead of creating jagged edges. And then finally we have laminated glass, which is what's found in car windshields. There's a piece of plastic that's sandwiched in between that window glass. If we're looking at glass at the crime scene, we can find it in shoes or carried on the clothing. And this glass can be used to identify a vehicle, match it up to a particular vehicle if it's questionable whether or not a vehicle was at a particular crime scene. If we're looking at bullet marks, remember from Crime Scene University, the instructor there was teaching how to figure out which shot was fired first. You're looking at right here, these lines. So you have these radial lines, and what you see here is that this line here was stopped, and this line here was stopped. It didn't shatter farther than that. So what we can infer here is that shot A was put into the glass first because its lines, its radial shatter lines, extend out farther and actually stop the shatter lines from B. When we're analyzing glass fragments, they can be put together like a puzzle. That is very time consuming though. Probably not very fun to do. We can look at the refractive index. So how does this particular sample of glass refract or bend the light? In this case, in the picture, light is bending through the glass at the same angle as the liquid it's dropped into. So since that refraction is the same, in essence it becomes invisible. We're not going to use this formula either though. Density gradient column is what we're going to simulate. It separates glass out based on its density using liquids of different densities. So what we see here, the glass pieces float at the density level that matches. So we have this, what we call a density column, liquids of differing densities. We drop some pieces of glass in, and over time they will settle at the level where their density matches. Just a little reminder of how density is calculated: mass divided by volume. Remember that when we're talking about a glass fragment, that's solid volume, but we're going to use liquid volume to help determine that volume. So 1 milliliter, keep that in mind. 1 milliliter is equal to 1 cubic centimeter. Also keep in mind the basic units of mass, volume, and density. So the basic unit of mass is the gram. For volume, it's the liter. And then density is grams per liter. A lot of times in this class we're going to use milliliters for volume and then grams per milliliter for density. And if you haven't used this triangle before, it's very helpful when you're calculating using the density formula. You're going to cover up whatever you're trying to find. So if we're trying to find density, then we know, okay, then mass is above volume. So you're going to take mass divided by volume. If you're trying to find mass, cover up mass. Now density is next to volume, so you're going to multiply those together. If you're trying to find volume, now mass is over density, so we take mass divided by density. That's how you use that triangle to help you remember how to solve problems with that. Then finally, if we're trying to find the volume of irregular objects, it's called the volume displacement method or the water displacement method. How do we find the volume of this irregularly shaped scuba guy? So we take the volume of water, a set volume of water. In this case it's 3.4 milliliters. We're going to see how much we drop the scuba guy in, the level rises to 5.0 milliliters. We're going to read at the bottom of this little curved area called the meniscus. So we subtract 5.0 minus 3.4, and that's the volume of the scuba guy, 1.6 milliliters.